So here now, what we're going to be doing in organic chemistry is continuing on and talking about individual functional groups. So we have been talking about thus far kind of a more broader aspect, things like nomenclature and stereochemistry and things like that. And pretty much what we're going to see from here on out until the end of 335B is this cycling through, and we're going to be talking about individual functional groups and talking about their chemistry. So really what the first one that we start with is halogens. And this leads us into a discussion about nucleophilic substitution reactions. And these are probably the simplest reactions to talk about, and they are probably the most versatile and the most common reactions. So it's a really good place to start talking about. So you will see more about what I mean later on. We'll talk about other ways that we can do reactions with halogens, and then we'll get into reactions that involve alcohols. But really what we're going to be talking about right now is nucleophilic substitution reactions. So what do we mean by nucleophilic? And so a nucleophile is actually, it means nucleus loving. So a nucleus, by this they mean the nucleus of an atom. And remember, a nucleus is made up of neutrons and protons. So a nucleophile wants to go attack something that has a positive charge. So with this, one of the things we're going to learn for it to be a nucleophile, what it needs is to be a Lewis base. So if you go back and look at our definitions of acids and bases, a Lewis base means it's a lone pair electron donator. So later on we're going to find out that plus or minus just about anything with a set of lone pair electrons on it can act as a nucleophile. And so it must have at least a pair of lone pair electrons to act as a nucleophile. So this is electron pair donor, and it's going to be going after electron poor sites. So that's what we mean by nucleophile. It's going after something positive. This means it's going to be going after something that is electron poor. And really that's going to be the other side. So what we're going to be talking about in the beginning are the nucleophiles, and there's a bunch of different types. And then we're going to find out that the organic molecules themselves are going to be the electron poor sites. And we're going to start off with halogens, and you're going to see as we go along through organic chemistry, we're going to talk about different types of nucleophiles, and then we're going to talk about different electron poor sites in different functional groups that we see inside of organic chemistry. So this is plus or minus what we're going to be talking about the rest of the year is nucleophiles, and we'll find out they're called electrophilic carbons here in just a second. So nucleophiles, they tend to be electron rich. So if you're going after something with a positive charge, it makes sense to have a negative charge. And later on we're going to define the difference between a good nucleophile and a poor nucleophile. Just to be a nucleophile, you need lone pair electrons, and to be a good nucleophile, you need to have lone pair electrons and a negative charge. And so there's always exceptions to these rules, but for right now, that's what we're talking about. So with this, the organic chemistry part is really going to be the electrophile, and we're going to find that there's many different ways that we can give carbons a slight positive charge. But in terms of our nucleophilic reactions, the electrophile is going to be a carbon, and we define electrophile as being electron poor. So it wants to go after something that's positive charge. So literally, most of these reactions in organic chemistry come down to something that's positive and something that's negative that is interacting. And it comes down to, well, how do you give something a positive charge and how do you give something a negative charge? And that's what we're going to be talking about the whole semester. So during the nucleophilic substitution, what happens is our electrophilic carbon accepts electrons from the nucleophile. The electrophile in this case is going to be a carbon, and we'll define that here in just a little bit. And in halogens, what happens is we go back to the idea of bond polarity. So in the first exam material, we talked about polar covalent bonds, and that when we have a covalent bond, we're sharing electrons. So here's a carbon-chlorine bond. This line represents 2 electrons, but they're not shared equally because the chlorine is more electronegative than the carbon. These electrons are actually shifted slightly towards the chlorine and away from the carbon. So this gives the chlorine a slight negative charge. So this is what this delta means. It means partial negative. And here, in doing that, it gives the carbon a partial positive charge. So the chlorine is pulling electrons away from the carbon. That's giving it a positive charge. That's what we mean by an electrophile. It has a little slight positive charge. So what we're going to find out is when we have a nucleophile, something with a negative charge and lone pair electrons, it's going to want to attack this carbon, and that's really where we get the reaction from. Also part of this reaction is what's called a leaving group. And so a leaving group literally does what it sounds like. It leaves during this reaction. So we're going to be forming a bond between our electrophilic carbon and our nucleophile, but our carbon is limited by only having 4 bonds. Remember the octet rule. So if I'm putting a nucleophile on there, something needs to leave. That leaving is a leaving group. And for right now, we're going to find leaving groups are mainly halogens. But of course, as we go along, we're going to find out there's other leaving groups. But for this part right now, our leaving group is going to be a halogen. So something needs to leave to avoid the octet rule, or breaking the octet rule. So we'll talk about what makes a good leaving group and a poor leaving group. But during this reaction, you're going to see overall its movement of electrons. So in organic chemistry, we don't change the nuclei. Carbons don't change to oxygens or anything like that. Really, during organic chemistry, all we do is move around electrons. And what we're going to see in a nucleophilic substitution reaction is electrons are going to go from the nucleophile to the electrophile, and they're going to run through the electrophilic carbon in this case. So we'll see this more in just a little bit. We're just defining terms right now. So you can see, and overall we'll see the thermodynamic graph for this. Overall, what we're doing is the nucleophile, remember it has electrons. Those electrons on the nucleophile are getting transferred to the leaving group. So the lone pair electrons, and in this case the negative charge, gets transferred to the leaving group, and we'll look at the mechanism here in just a second. And in the leaving group, this lone pair electrons and negative charge is more stable. So that was one of the things that we learned, is in terms of stability, halogens tend to be able to stabilize negative charges. And so that's overall why this reaction occurs, is we're going from the negative charge is going from a less stable to a more stable state. And so that it's kind of like going downhill, and that's why this reaction occurs. Also, our leaving group needs to be able to stabilize this negative charge, and we'll talk about a bunch of different ways that we can stabilize a leaving group, but for right now we're going to talk about halogens. Halogens tend to be very electronegative, so they tend to be able to stabilize negative charges, so they tend to make very good leaving groups. And so in the beginning, these are the leaving groups that we're talking about. Bunch of different leaving groups in the world, and we'll get to that a little bit later. So when we look at a typical nucleophilic substitution, so right now we're going to talk about specific types of nucleophilic substitution, but this is a generalized one. One of the things that you should be able to do is identify the 3 parts. The 3 parts are the nucleophile, the leaving group, and they call it the electrophile, but I really like to call it the electrophilic carbon, because with organic molecules there can be a large number of carbons. We're really interested in the electrophilic carbon because that's where all the chemistry takes place. So if we have 15 carbons, the only one that's really interesting is the carbon that is directly attached to the halogen. That is my electrophilic carbon. So the whole molecule is technically called the electrophile. I like to talk about the electrophilic carbon. So you need to find the nucleophile, the leaving group, and the electrophilic carbon. So here in the beginning, you can see the negative charge starts off on the nucleophile. And in the end, the negative charge ends up on the leaving group. Most of the time in the beginning, the leaving group tends to be a halogen attached to a carbon. And then my electrophilic carbon is the carbon that's directly attached to the chlorine. So remember, the chlorine's pulling electrons away from the carbon. That gives the carbon a partial positive charge. That's why this hydroxide now, it's lone pair electrons and a negative charge, wants to attack here. So if you look at it, if I add overall what we end up doing, and we'll look at the mechanisms of these in just a second. Overall, what we're doing is connecting a bond between the nucleophile and the electrophilic carbon. If I do that, I'm going to have 5 bonds. I'm going to be violating the octet. So we need to break a bond between the electrophilic carbon and my leaving group. And that's why we do that. And remember here, our carbon starts with 4 bonds, ends with 4 bonds. And now you can see why it's called a substitution reaction. Really what you're doing is replacing a halogen with a nucleophile. And for right now, this is going to be the interesting part, is there's a lot of different nucleophiles. I'm going to give you a short list, and we're going to add to this list of nucleophiles throughout the whole year. By the time we're done, we're going to talk about several different nucleophiles. But that's really the power of this reaction, is I have a lot of variability in terms of my nucleophile. So here I was able to turn a halogen into a alcohol during this reaction, and by changing the nucleophile I can get different functional groups out. So what I'm going to do now is talk about some common good nucleophiles. So the idea is there's a very long list of nucleophiles. What I'm going to do is give you a basic list, and you just need to know these. And really what we're going to do is talk about the different flavors of nucleophiles. So the nucleophiles are not all the same, and we're going to kind of expand on this, and there's going to be different factors involved with them. So I'm not going to give you a very long list. I'm just going to give you the very common ones, and then we're going to work with these. So common good nucleophiles, the first one's hydroxide. So we've already run into this in 115. It's really deprotonated water, and it's HO, and forgive me, there should be a negative charge here, so it's a good nucleophile. Lone pair electrons and a negative charge. Another one is called an alkoxide. So we haven't talked about this, but we're going to be talking about this a lot. This is one of the most common type of nucleophiles, and what an alkoxide is, and I don't know why my negative charges aren't showing up, but sorry about that. A deprotonated alcohol is called an alkoxide. So the same here we made an hydroxide. So oxide means a negatively charged oxygen, so there should be a negative charge here. I removed a hydrogen from water to form a hydroxide. Here what we're doing is removing a hydrogen from an alcohol to form an alkoxide. So here, and once again, sorry, there should be a negative charge on this one and this one. If I took off a set of lone pair electrons and put a hydrogen on there, that would be methanol. And we'll later on talk about, well, how do you deprotonate an alcohol? We'll talk about that later in kind of near the end of the semester. But for right now, alkoxides, in this case, I only really expect you to know two. Methoxide and ethoxide. So an alkoxide is kind of a functional group, and these are specific examples. Methoxide is where there's a methyl group coming off of my oxygen. Ethoxide means there are two carbons coming off of my oxygen. These are among some of the most commonly used nucleophiles that we know about. So remember, alkoxides just mean a deprotonated alcohol. Methoxide and ethoxide are specific examples of alkoxides. One is made from methanol, one's made from ethanol, and then these are our common good nucleophiles. So here we can look at another example of what we're talking about, and the idea here in organic chemistry is, and I'm going to say this about 50 times, it's similarities and differences. You want to be able to look at what's going on and say, how is this similar to what we've been looking at, and then how is it different than what we've been looking at. So here, this is still a substitution reaction, like the one we just looked at, but now instead of hydroxide, we have an alkoxide. And really the only difference is, in here in this bond, instead of it going to an H, it's going to a CH3. Everything else is the same. This is my nucleophile, my oxygen with lone pair electrons and a negative charge. This is my my electrophilic carbon is the one attached to the halogen. My leaving group now is a bromine instead of a chloride, and once again, I don't know where my negative charges went. The bromine should have a negative charge. But what we're going to learn is during this reaction, what we end up doing, and this is kind of the way I like to look at these reactions. I say, what do I have to do to the reactants to get to the products now? And draw the product of the reaction, and we'll go over this a bunch, but this is really what I want you to be able to do. This is a classic question in organic chemistry where I give you the reactants and you want to be able to tell me what the products are. Really what happens is I connect my nucleophile to my electrophilic carbon. So you can see we form this oxygen carbon bond here. So this oxygen used to be here, this methyl group used to be here, and then remember this CH2 used to be my electrophilic carbon. So we connect a bond between my oxygen and my electrophilic carbon, and then we break the bond between the carbon and the leaving group. So it's a substitution reaction. I'm substituting the leaving group with my nucleophile, and during the process my oxygen loses its negative charge. The negative charge gets pushed over to the bromine, But here, between the first reaction and the one we're seeing now, all I did was change a hydrogen to a CH3. So the overall steps that I use to get from the reactants to the products is the same. It's just instead of a hydrogen down here, I have a CH3, and instead of making an alcohol, I've made an ether in this case. So you begin to see the power of the substitution reaction. By changing my nucleophile, I've changed my product. I've changed the functional group that I'm able to make. In the first example, I made an alcohol by reacting with my nucleophile hydroxide. Now I've made an ether by reacting with my nucleophile methoxide. And notice my electrophilic carbon really hasn't changed. It's still going to be some carbon chain. Electrophilic carbon is the one attached to the halogen, and the halogens can change. Typically we see like chlorine, bromine, and iodine. That's really the difference. So the idea is you see this pattern, and this is going to be the same. The only thing that's really going to change is my nucleophile, and then maybe how many carbons are coming off my electrophilic carbon. That doesn't really matter at this point. I kick off my leaving group, I replace it with my nucleophile. That's why it's called a substitution reaction. So another good nucleophile is called the Cyanide Anion. And once again, I don't know where my negative charge is at, so there should have been a negative charge on this carbon, so my cyanide should look like this. But the Cyanide Anion is another good nucleophile. And the same thing here, that it's just this repetition. What do I do to go from reactants to products? So I still have a carbon chain, I still have a carbon attached to a halogen. My electrophilic carbon's this one, so remember to learn to really focus on the electrophilic carbon, the one that's attached to the halogen. These methyl groups here coming off really don't do anything at this point. They come along for the ride. This is my electrophilic carbon, and this is my nucleophile. So the nucleophile is the one with the lone pair electrons and negative charge in the beginning. What do I end up doing is I kick off my leaving group, bromine. My leaving group gains a negative charge, and I connect my nucleophile and my electrophilic carbon. So we end up forming this carbon-carbon bond here during this reaction. And we'll see how the electrons move in a little bit when we see the actual mechanisms. When we start showing arrows, it might be a little bit more clear. But really what we're talking about is substitutions in general, and different types of nucleophiles. So the last couple of one's called a Hydra sulfide anion, and once again, there should be a negative charge on this sulfur here. Sorry about that. And we'll see some examples of that. And the last one is kind of a very common nucleophile. It's called a carboxylate. And notice how when we made hydroxide, we removed a hydrogen from water. When we made an alkoxide, we removed a hydrogen from an alcohol. To make a carboxylate, we remove a hydrogen from a carboxylic acid. So very much like hydroxide and alkoxide, carboxylates are these negatively charged oxygens with 3 sets of lone pair electrons. And the idea is if I exchange the lone pair electrons with a hydrogen, what I would have started with is a carboxylic acid group. So here I deprotonate a carboxylic acid, I end up making a carboxylate, lone pair electrons and negative charge. It makes a good nucleophile. And the idea is we'll look at some other of these, but you should be able to tell me what the product of a nucleophilic substitution reaction with one of these, and we'll see some examples of it later. But it's exactly the same. All I'm changing really is the nucleophile. The process is going to be the same despite of the nucleophile. I kick off the leaving group, I replace it with my nucleophile, and all this takes place on the electrophilic carbon.